This is problem number 5 from chapter 12. The problem reads, a stone is dropped from the cliff. The splash it makes when striking the water below is heard 3.5 seconds later. How high is the cliff? I've made a sketch of it over here on the left. We can see the stone is initially dropped. It accelerates down to the water surface. The splash makes these kind of sound pulses that then travel back up at a constant velocity. These are sound waves. I have two separate equations here. The first one is an equation that models kind of number 1 in red here. This is the accelerated motion, where I can say that delta y, or more specifically h, because that is delta y, is equal to VOT plus 1/2 AT squared. This is the first equation of motion, and the initial velocity is 0, so I'm left with h is equal to 1/2 AT squared. I also need to make some adjustments to this. The first one that I'm going to make is change a to g. This is gravitational acceleration. I'll deal with the negative sign later. All that's going to do is tell me that h is in the downward direction. And t specifically is the time on the way down. Because we'll see here in just a second that I'm also going to get time on the way up, and that's a different time, so I don't want to confuse those. So step number 2 would then be modeling the speed of sound. Velocity is equal to distance over time. So I can say just kind of in general form here, but the distance that it travels is the height of the cliff, and the time that it travels is the time on the way up. Okay, so what I'm going to do is start with this particular expression. H is equal to 1/2 g times t on the way down squared, but I'm going to replace the t on the way down with a different expression, and that's going to be total time. I'm going to call capital T. That's this one, the 3.5 seconds that I know about, and I'm going to multiply that by, subtract that from T up, and I need to remember to square that. So of course, T total minus T up is equal to T down. That makes sense. And I can make another expression for T up. T on the way up, if I kind of deal with equation number 2 here, is going to be the height of the cliff divided by the velocity of sound. And ultimately, I'm going to substitute this right here in for T up right here. Let's go ahead and do that. So now I get h is equal to 1/2 of g times my total time t minus h over v sound. I need to remember to square that. I'm not going to put the subscript. I mean, I could hear the v sound, but it's the only velocity that I have in this problem that I'm dealing with, so I'm just going to leave it out in my future steps just to kind of clean up the algebra here and make it look a little easier to see. So what do I do next? Well, first of all, I need to acknowledge that this new expression has eliminated all of the unknowns, which were time on the way down, time on the way up. These are things that I didn't know, and through a series of substitutions, I was able to eliminate them. I'm going to multiply both sides by 2 and divide by g. That's going to take care of that guy right there. And so I'm going to get 2h over g is equal to, now I'm going to FOIL this thing out. So I've got t minus h over v squared. So my first is going to be t squared minus t times h over v minus t times h over v plus h squared over v squared. So I basically FOILed this out. Of course, on the right hand side, I'm just going to combine those two middle square terms. So I get t squared minus 2t h over v plus h squared over v squared. Now, I'm starting to see something that looks like a quadratic. I've got, my x squared, my higher power here, my x, h is basically the root ultimately that I'm looking for, and finally my constant c over here. So let's go ahead and rearrange this thing. I'm not going to touch what I have on the left. I've got 2h over g. I'm just going to reorganize everything on the right hand side. So I'm going to get h squared over v squared, and I need to subtract from that my middle term 2t times h over v, and then finally I have to add that, my constant t squared times v squared. Both of those are known, so it's just some number. And I'm going to isolate, I want to isolate h squared, the higher power here. So I'm going to multiply both sides by v squared. So what I get then is 2 times v squared all over g times h. H is in the numerator. I've kind of separated it out here on purpose because, well, we'll see here in just a second. And on the right-hand side, I get h squared, and I got to subtract from that 2t times, now I multiply both sides by v squared, so the v in the denominator is going to go away. I'm going to be left with 2v times h. And then finally, my constant t squared, v squared. So the last thing that I need to do is I'm going to deal with this on the left-hand side. This term, I need to set this equal to 0, so I'm going to subtract that from both sides. And so now I get something that looks like this. I get 0 is equal to h squared minus 2tv, that kind of sounds funny, tv, times h minus 2v squared over g times h plus t squared v squared. Now I want to factor out this h. This h is the middle power of my quadratic. So I'm going to get 0 is equal to h squared. I don't have to, but I'm going to go ahead and take out the 2 and the v, since one of those appears in each term. And so therefore now I get t, and since I took out a negative 2, this becomes the first term. What's left is t, and this is plus v over g times h. That's a bit tricky. I think that's the hardest part, at least it was for me. So I took out a 2v, and that's what I have left. That's my binomial expression, and then nothing is affected in my last term here. I get t squared v squared. Okay, so it was kind of a beast, and you should recognize this looks familiar. This is in the form ax squared plus bx plus c, where my a value, let's go ahead and define these. My a value in this case is going to be 1. My b value is, when I plug this in, it's gonna be funky because I have a bunch of substitutions to make here. My b value is going to be negative 26,411. 26,411, and that's negative. Oops, hopefully you can see that. And my c value is going to be obtained by squaring t, which is 3.5 seconds. That's the total time times the speed of sound, 343. And I need to remember to square that. And so my c value then becomes quite large, 1.4412. 1.4412 times 10 to the 6th. So I have a pretty significant number here. Those units, by the way, are going to be meters squared, and my b units are going to be also are just going to be meters. Okay, and I'm going to plug that into a quad solve and get 2 roots. The 2 roots, the first one is very large, 26,000. So I get 2 roots. H1 is equal to 26,356 meters. And my second root in my quad solve is 55 meters. Now, from intuition, I'm being drawn to one of these, but let's also acknowledge, hey, if this was actually 26,356 meters tall, then it's going to take more time for it to just fall down. You can run that through one of your kinematics problems. So it's going to take way more than 3.5 seconds just for it to fall. So that's not it. That's not one of my plausible roots. This is. The height of the cliff is 55 meters tall.